Hi, welcome back to day 7 of this course, our Calculus AP course. Today we're going to discuss the graph of the derivative function. Keeping in mind that the derivative of a function just represents the slopes of the tangents of some function f of x, the derivative function then just describes all those tangents. So if we take a look at this next page, I've just shown you for some clarity here that given y equals x cubed, its derivative using the power rule would be 3 times x squared, bringing the 3 down and reducing the exponent by 1. And I've graphed the parabola, 3x squared. Now, just so you can see, taking a look at this one tangent here that I have, this green one, which is approximately been drawn at, you can see the tangent line to x cubed is around x equal to 1. The slope of that tangent looks to be around 2. And sure enough, at this point here, the parabola is around 2. Likewise, at negative a half here, the slope of the tangent looks to be around 1. And so at negative 1, if we go up to the parabola, we see sure enough the value is 1. All right. This next website may or may not work for you. It doesn't work in native Chrome, so I use Waterfox and grant the site permission in the Java configuration because it's a Java applet. Or you could get the IE tab extension to Chrome. Either one should work. So if I click on this link here, they used to have some interesting puzzles on here, but the only one that seems to be working now is this big derivative puzzle. And when you do that, let's move this over a bit. The idea here is they've shown 4 graphs at the top, in the top row, and the 4 graphs at the bottom represent their derivatives, but not in order. And so you have to place them by taking and dragging them. And when you say evaluate, it will mark you, and depending on how many times you move things around, it reduces your score. Anyway, a good way to reason this is, let's see, this second one here, for example, is a cubic, so we know that its derivative would be quadratic. There are 2 quadratic functions here, but given that the behavior of the second one here is from Q3 to Q1, the leading coefficient must have been positive. And so it must be the parabola with the leading coefficient, which is positive as well. So I think that this one probably belongs there. This next one, the third graph here, also looks like a cubic, except it's going from Q2 to Q4. Its leading coefficient must have been negative. And so its derivative would also be negative, and a parabola at that. So this one must be going here. The first one is a parabola, and you notice that its leading coefficient must be negative because it opens downwards. So when I take the derivative of a quadratic with a leading negative coefficient, I'm going to get a linear function, and its slope would be negative. And so that would be this one. And then from the process of elimination, this one must be that one. And once you've done that, you notice it tells you at the top there what your marking is there, that they were all true. And if you say evaluate, it says in this case I got 10 out of 10. So it's a good thing to play around with. You can say load new, and it'll come up with some new graphs, some that you may not have seen yet. We'll be taking a look at sinusoidal curves some other time. So play around with this. It's great fun. It gives you a good appreciation for how a function and its derivative are related. All right, so let's close this up. Now, this says to draw a reasonable sketch of the derivative of this function on this interval. And it says, where's the function not differentiable? Well, you'll recall that functions are not differentiable at cusps and corners and asymptotes and holes and so on. Asymptotes and holes don't apply here, but corners certainly do. And so we can tell this function is not going to be differentiable at -2, -4. It's also not going to be differentiable at 0, 3. And also at this corner, which is at 5 and 3. What happens at the endpoints in terms of what this function is doing, we don't know because it hasn't been shown. So I've not said anything about those endpoints. Now, in terms of trying to figure out what's a reasonable derivative, we can see from this first line here that the run is 3, but the rise looks to be -2. So it's -2/3. And so -2/3 would fall about here. And for the next leg, going from the second point up to the third, it looks like the rise here is about 3 for a run of 1. So the slope looks to be around 3. And so 3 would be right here. Oops, that didn't come out very well. Let's fix that. There we go. And I probably should have done this in a different color. Then it would stand out better. So let's just change the color of this. That's better. And this segment as well. Okay. And across the top here, between the third and fourth dot, the slope appears to be 0, because it's a horizontal line. And so that would look like this. And then finally, between the fourth and the fifth point, the slope is negative, and it looks to have a drop here of 3 for a run of 1. So the slope is -3. So that would be about, let's see, about here somewhere. So there's a reasonable graph of what the derivative might look like. All right, moving along. Now, you want to look at this. This is looks like a quartic. I just got 3 humps here, 3 transitions, so it's a quartic. It's going from Q2 to Q1. And so its derivative is going to be cubic. So draw a reasonable sketch of what you think the cubic might look like based on where you see these transition points taking place. I'll give you a hint. Those are horizontal tangents there. And so see if you can come up with a reasonable attempt at graphing its derivative. You might want to pause the video here and try it on your own. And when you come back, you can take a look at the answer. So I've covered it up here. And so if I delete this, you can see what the derivative looks like. So wherever the quartic had humps or horizontal tangents, which occurred here, here, and here, that means that at those points, the derivative will have x-intercepts. So one there, and one there. And given that it's quartic and a positive a value, the leading coefficient is positive because it goes from Q2 to Q1, I know that the cubic will also be have a positive leading coefficient, and so it'll go from Q3 to Q1. And so this graph would have to come up like this, go through there, turn around, go through there, and then go up. So that's a reasonable facsimile of the graph on the right-hand side. So here's another one. This time we're working backwards. So I've given you the derivative, and it says sketch a possible graph of what f of x must look like. Again, you may want to pause the video, analyze this, and see if you can come up with what f of x might look like. All right, if you've returned, the way to reason this is the derivative function. So wherever it has zeros, namely at here, here, and here, f of x must have horizontal tangents because its slope would be 0 at that point. So given that this is a cubic function, right, it's something cubed, f of x must have been quartic. So maybe I'll just make a note of that here. So f prime of x is cubic. So f of x is quartic. And given that it's quartic, and the cubic here happens to have, is going from Q3 to Q1, so its leading coefficient's positive. So the quartic must also be have a leading coefficient which is positive. And so its shape, for a quartic would be something like this. So you could draw this. You just want to make sure that it has horizontal tangents, namely here, here, and here, wherever the cubic has its zeros. So one way of drawing this then would be wherever you see the x-intercepts of 0 here, you want to have a bump in the quartic. So we could be coming down, going like this. And then going up again. We're doing this without any analysis of what the y-intercept was and that kind of stuff, or looking at the equation and looking at the zeros and coming up with an equation. This is just to try and come up with what do you think it looks like, just roughly, based on what you're seeing. All right, so determine whether the following function has horizontal tangents or not. Well, the function is a quartic. The coefficients have been made up, so something nice happens when you take the derivative. So f prime would be, the 4 comes down, 4 times a quarter is 1, so it'll be x cubed, minus the 3 comes down, multiplied by the 5/3, that produces 5, x squared, plus the 2 comes down, multiplies 7/2, produces 7, x minus 3. Now, this is the derivative function. And if we're going to be determining whether it has horizontal, if the original function had horizontal tangents, we want to see where is f prime equal to 0. Well, the only place it could be if it had zeros would be factors of this. So this thing must be some sort of quadratic times a linear term, or it could be the product of 3 linears. Anyway, the only thing to test then, given that the constant there is -3, the only things we need to look at are plus and minus 1 and plus and minus 3. And then using, if you've learned the factor theorem in your earlier days, we'll try f prime of 1. And if you do that, you'll see it equals 0. That's a good thing. So that tells me that there's a horizontal tangent at 1. Next one, if we do f prime at -1, this turns out to be -2, so that one's no good. If I do f of 3, I also get 0, so that's good. And f of 4, oh sorry, not f of 4, f of -3, silly me, f of -3, because these were the only factors of -3, plus and minus 1, plus and minus 3. And this turns out to be a very large number, negative. It's certainly not 0, so this is no good. And so, given that f of 1 was 0, we know that x minus 1 must be a factor of this. Likewise, f of 3 is 0, So that means there must be another linear factor in here of x minus 3. Oh, sorry, I made a mistake there. That should be x minus 3, but this doesn't make sense. Oh, so then this other factor here must be x minus something to produce that negative 3 that's there. Everything's looking good. All right, so given that this is the derivative, it says determine whether the following function has horizontal tangents. Well, the answer would be at x equal to 1 and x equal to 3. And this is a quartic, so its derivative would be cubic. And so we know that at 1 and 3, we're going to have zeros. And so this function must be coming up, going through here at some point, turning around, and then going through there. Okay? I've covered up the graph just so that you could determine where the horizontal tangents were just by looking at the equation. So if I get rid of that cover-up piece, the blue one is f of x, and the red one is f prime. And you can notice that it had zeros at 1 and 3, as expected. Okay, so those would be the locations of where the horizontal tangents are occurring on f of x. And you can see that here, because one of them's right here, and one of them's right here. Okay, approximately. All right. Does this function ever have negative slopes? Well, I guess the first thing to do is to determine what the derivative is. So f prime of x would be 5x to the 4th minus 21x squared. And the question is this thing ever negative? Well, could be, depending on the value of x, I suppose. Well, I can factor an x squared out and see what happens. We end up getting 5x squared minus 21. And looking at this expression in terms of will it ever be negative? Well, this will certainly never be negative. This is never negative because it's something squared. But this could be negative. You know, if I put x equal to 0, for example, I get a negative quantity. So it could be negative. So if we set that to 0, minus 21 is equal to 0, we end up getting x squared is equal to the square plus and minus the square root of 21/5, which is equal to plus or minus 2.04. So at plus 2.04 and minus 2.04, we have horizontal tangents. Given that this is x to the 5th, this is a quintic function, so it must look like, all quintics look just like x cubed does, for example. It would look, something like this, have this sort of behavior, but it'll have more bumps in it than this as a result of being x to the 5th. So it would possibly go like this, like that. And so does it ever have, it possibly looks like this. I haven't analyzed it enough. But does it ever have negative slopes? Well, yes, it does. In order to have these transitions, it must have them. So let's take a look at the result here. If I get rid of this. So there's the graph of that function f of x. And sure enough, you see we have a horizontal tangent right here at 0, right there at 0. Let me just draw that in here. We have a horizontal tangent at -2, 2.04, one at positive 2.04. And we said, x squared was one of the factors here. So at x equal to 0, we have a horizontal tangent, which you can see. And so does it ever have negative slopes? And the answer is yes. It's happening here, and it's happening here. So once you've got the 2.04s done, then you know between negative 2.04 and 0, and then again between 0 and 2.04, it must have the negative slopes. This concludes the lesson on the graph of the derivative function. I hope you get a chance to play around with that website and predict or to match up derivatives with their functions. If you can do that successfully, then you've learned the lesson presented in this session well. Take care. See you in the next one. Bye.